Hello everyone again. This is Jim Malis again. I haven't changed. Still me, Jim Malis. Here we go. Let's talk a little bit. We talked last time, we left off on the last three problems from chapter 4 that I wanted to talk about. We left off and hadn't really completed them. We left off at problem number 60 in the last video from chapter 4. And so we're going to finish chapter 4's problems. Problem number 60, we're going to finish right now, then we'll do 68, then we'll do 70. And that'll take us through chapter 4 that we wanted to say. Well, how did it go, you guys? Did you actually get a chance to look at what I asked you to look at? Were you able to finish what I asked you to finish, or at least ask you to try if you get a chance to do so for problem number 60? Let's talk about it. Let's read it again, and let's see where we are vis-a-vis all this stuff, you guys. So, For problem number 60, a golfer hits his approach shot at an angle of 50 degrees, giving the ball an initial speed of 38.2 meters per second. The ball lands on the elevated green, 5.5 meters above the initial position near the hole. 5.5 meters above in the vertical direction, 5.5 meters more vertically located than it was initially. So it's 5.5 meters above what it was initially near the hole. And it stops immediately. There's A, B, C here for questions, you guys. How much time passed while the ball was in the air? A, how much time passed while the ball was in the air? B, how far did the ball travel horizontally before landing? C, what was the peak height reached by the ball? So, I mean, like I said, that's essentially it. They're asking us, A, how much time passed for the whole flight to occur. How much time passed, that was A. B, how far did it go in the horizontal sense? And C, how high did it go? So, what was the total time of the flight? For B, what was the actual physical distance traveled in a horizontal sense? Just drop a perpendicular straight down, drop it straight down. What is that horizontal distance? That's B. So you want to know the time, the total flight time, the horizontal distance, and you want to know the maximum height that's attained. Well, what we said last time is what we're going to continue to say basically. If you want to know the total flight time, there are going to be two times where the height's going to be this high. It's going to be 5.5 meters high right here, and then you come across here, and it's going to be 5.5 meters high over there. The time it takes to get 5 meters high right here is not a whole lot because it's in the initial part of the journey. Toward the end, it's going to take more time. It's got quadratic equation written all over it, like we said last time. So if that's the case, let's talk about it a little bit. We know that number of ways you could actually talk about this, I guess you could say. We know that the distance can be written as something of the form VIT plus 1/2 AT squared. Well, in this case, the distance is height. In this case, the VI is the VYI, the V naught Y going upward, and A happens to be a negative number because you are going up and down, and in that case, acceleration due to gravity, you've got to call it negative. So, it's as simple as that. You want to know the height, 5.5 meters, with V0Y initially going on upward. There's a time, there's plus negative 1/2 GT squared. 5.5 is the height you want to get, that's D. 38.2 is the initial speed given to the ball. The vertical projection is 38.2 times the sine of 50 degrees. You're going to multiply by time t, a flight time under consideration, and you're going to add 1/2 times a negative 9.8 times t squared. 1/2 times negative 9.8 is negative 4.9. Get everything over to one side, set it equal to 0. There's a quadratic equation being set up here, obviously. Here's your quadratic equation. Proceed. T is going to be equal to all of this. There's a plus or minus scenario here. Here's a big amount of time. Here's a small amount of time. The small amount of time, about 0.2 seconds, 0.194 seconds. It took about 0.2 seconds to get up to here. Here it took about 5.778 seconds to get over to the other place. They're both associated with a height of 5.5. In about 0.2 seconds and in a little bit less than 6 seconds are the two times that tell you what happens. Scenario 1, how long does it take to initially reach a height of 5.5? 0.19 something seconds, about 0.2 seconds. How long does it take to get to 5.5 again? So 5.5 initially took about 0.2 seconds to get there, initially hit. Then the flight journey will bring it back to 5.5 elevation, and that will happen a little less than 6 seconds later, 5.778 seconds. So the time, we don't really care about this one, but we got it. We do care about that one, and that's A. Then we plug in that A, that value of time, 5.778 seconds, you put it right here. You put 38.2 right here, you put the cosine of 50 right here, grind it out, you got to here, you got to here, you got to here. This will tell you the horizontal distance. What do we say about horizontal distance? The components of velocity operate independently of one another. The components of velocity operate independently of one another. The x component of velocity remains unchanged. We're not assuming no air resistance, nothing funny, no funny business here. It's just no air resistance, ideal situation, what's going on? What is going on is, as we said, it's going to be a constant horizontal velocity component times the time. It's as simple as that. 141.876 meters. Pretty good drive. That's a pretty good drive. So they drove it pretty far to get it to go there. The time we said was 5.778 seconds. X, the range in the horizontal sense, is 141.876 meters. How high did it go? We already derived this in earlier work. This we already derived in earlier work. Let's plug everything in as we should. V0 squared sine squared theta. Here's V0. Here's sine theta, the whole quantity. Square it. It's the same as V0 squared sine squared theta. Divide by 19.6. How high does it go maximum? 43.69 meters. Okay. This is kind of what I had asked you to do last time. I hadn't gotten the specific numbers. A few of these problems, I'm assuming I've done this maybe throughout much of the discussion that I'm going to do. I guess we'll find out. I haven't looked at it too carefully. I've given some of these problems something I was pretty much going to do cold without some of the notes in front of me. So I wanted to kind of double check where I was going with some of that stuff. But this is where you're going. Looks pretty good, you guys. It's a really good problem. It's an excellent problem. See what else we can say here. There is problem. Okay. Let's look at problem number 68. Problem number 68. Frequently a weapon must be fired. Problem number 68. Frequently a weapon must be fired at a target that is closer than the weapon's maximum range. So we're assuming here this is before the era of maybe of higher technology or something like that, or even now, even current. I don't know. I'm not an expert in these sort of matters, but there's a situation where there's going to be a maximum amount of velocity that occurs. There's a muzzle velocity associated with something being fired, whether it's a rifle, whether it's a howitzer, whether it's some kind of cannon, whether it's whatever, some sort of artillery piece that's being fired. Once it is fired, it's a projectile, and because all the shells are, let's say, for our circumstances that they're talking about, have all the same capabilities, they don't really change. Well, if the thing's going to fire 5 miles, and you just want to fire at a target that's 1 mile away, somehow the way the firing of the weapon is directed has to be modified because you're not going to really change the range. The range is 5 miles, and if you fire it in such a way that's going to maximize the range, you're not going to hit a target that's 1 mile away. That's kind of what they're saying right here. So they're doing a couple things here. It's kind of a long discussion pertaining to it. So let's start talking about it, I guess you could say. Problem number 68. Frequently, a weapon must be fired at a target that is closer than the weapon's maximum range. To hit such a target, a weapon has 2 possible launch angles, one higher than 45 degrees and one lower than 45 degrees. Theta sub h and theta sub l, you guys, the way they describe it in the book. Although the displacement of the projectile is the same for the 2 angles, a projectile launch at theta sub h has a higher flight time, a longer flight time, and a higher peak position than one launched at theta sub l. Usually some tactical situation makes one angle preferable to the other. For example, if the projectile must go over some nearby object, such as a grove of trees, the higher angle may be desirable. A shorter flight time and therefore theta sub l are preferable if the target is mobile. In practice, many weapons are designed to operate either at angles lower than 45 degrees or at angles higher than 45 degrees, but not both. Tanks, for example, must face mobile targets. To minimize the time the target has to move, tanks fire at low angles. Grenades, on the other hand, are launched at high angles because a soldier launching a grenade is often close to the target, but has no armor plating for protection. The high launch angle allows the soldier to stay out of sight by hiding behind some obstacle, and the longer flight time may make it possible for the soldier to move farther from the exploding grenade. Okay. Imagine an unusual scenario in which a large gun mounted on a vehicle is required to hit an explosives factory. A huge explosion is expected, and there must be time for the gunner to retreat. A grove of trees provides cover. The maximum range of the gun is 17.6 kilometers. Pretty far. It's more than 10 miles, you guys, like 11 miles. 17.6 kilometers, and the maximum speed of the vehicle is 80 kilometers per hour. A, what is the muzzle speed V sub 0? Muzzle speed is the speed at which the projectile leaves the barrel of the gun. That's A. B, the target is 5.5 kilometers away. Find the low angle theta L and the high angle theta H at which the gunner must aim so as to hit the target. C, find the time the projectile takes to hit the target for both angles. D, assume the angle retreats at its maximum speed of 80 kilometers per hour to be as far from the ensuing explosion as possible. How far is it from the factory at the time of the explosion for each launch angle? So A, B, C, D, and 2 parts on every single one of those. That is a long problem. Guys, the problem itself, to read it, is half a page long. I can't read it again, but you've got the book. Look at it and kind of compare what I'm doing when I am doing that. So let's see what we have here, guys. They're giving different scenarios. They talk about different things. Let me just kind of write out the notes verbatim and kind of walk you through it, and I think we'll be okay. Let me just see here really quickly. And again, guys, all of this is in the notes that I've provided for you if you're in my Physics 209 class. So that'll help as well. It is about, I don't know, it's on the order of maybe 5 to 8 pages here. So let's, then again, I write very largely, so it shouldn't be too bad. Let us see how we can kind of talk about this. So let me erase what I did write earlier, and we'll kind of take it from there on that. So for problem 68, All right, guys. Let's run through it. It's a load. I mean, that's for sure. What we can say is try to modify a bit. I guess you could say for the two different angles here. Maybe I can shorten this up a little bit for you, make it a little easier. You've seen me do these arguments. You already saw me do the basic argument. You've seen me do the basic argument for how to proceed with projectile motion. You've seen it. I've given the general argument for it. The problem that we just did was an excellent example of what goes on to a good extent, to a large extent. Things I showed earlier are a good example of it as well. So let me not repeat those as much. Let's just kind of say this. Let's say some things we already kind of know, we already derived. The time to get to the peak is small t. That's v sine theta. V is vi, v is vi or vo, whatever. Let's call it v right now. That's the time it takes to the peak, to reach peak. To do the full journey, it's double that. So it's t to go up, t to go down. Therefore, the total flight time total flight time. And we got that. Okay, this thing's being fired. The range, there's a whole bunch of song and dance that goes with that. We know that the range, max range, whatever, just range in general, R or X, I'll call it R this time, I call it X other times, is V sub X times the total flight time. Times the total flight time. So, true. What does that mean? Well, it means a lot. I mean, it means R is V cosine theta. That's the X. That's V sub X. That V sub X is V cosine theta. T is the total flight time. Total, that means up and down. So it's 2V sine theta G. There's the whole song and dance that proceeds from here. We've got V squared 2 sine theta cosine theta over G. There is some beautiful trigonometry that goes on that tells us that 2 sine theta cosine theta is just sine, 2 sine theta cosine theta is sine 2 theta. So what do we got? I mean, at the end of the day, we got what we already know. Arguably didn't even need to go that far. We've already seen that in previous work. But here it is. That's the range, that's X, you can call a lot of stuff to get it through there. We know that the maximum range is going to occur at theta equals 45 degrees. Now, we don't need the maximum. The maximum is going to be 17.6 kilometers. And that the 17.6 kilometers is attained when theta is 45 degrees. 17.6 kilometers. We don't want that. We're looking to go, I guess you could say we're looking to go a lot less than that. Yeah, in the meantime, let's figure out how fast that thing, let's actually do what we do know. Can we talk? They want us to find the muzzle velocity, plain and simple. That's A. To find the muzzle velocity, we got to find what V is. How the hell are we going to do that? Well, I mean, there's a lot of stuff going on. I tell you what, let's make life easy. Let's put a 45-degree angle right here for theta. 45-degree angle. 2 times 45 degrees. 2 times 45 degrees is 90 degrees. The sine of 90 degrees is 1. We got, for the max, we've got this, the maximum range. And that's the maximum is going to occur like that. Well, we know a lot. I mean, we can essentially let us just do that. Let me multiply by, let's look. This stuff is easier done than me delivering a speech sometimes. I mean, it's just, let's get it from there. Right here, what you got is you got v squared equals g r max. Let's just multiply by g. Multiply by g on each side. When you multiply by g on each side, you get to here. Square root both sides. Right here, you end up getting v equals the square root of gr max. If you put 9.8 meters per second times 17.6 kilometers, you're not going to use 17.6 kilometers. You're going to convert to meters. 17.6 kilometers is 17,600 meters. 17,600 meters times 9.8 meters per second. Get an answer, square root it. It is essentially, let me just write this. Yeah, it's coming out of, according to what we're saying here, speed of sound's about 343 meters per second. This is going substantially faster than the speed of sound coming out, the muzzle velocity. So 415.31 meters per second. And that is, that's this, that's A. That's what it is in both instances. Now, okay, good to know. Now what they're saying, we will find two angles between 0 and 90 degrees, theta sub L and theta sub H, that satisfy the particular conditions for a given scenario for R equals V squared over G times the sine of 2 theta. 550 meters is R in this case. So, this is what it is, guys. It's definitely what it is. So, here's your scenario. In this case, they're trying to find the two angles where that's going to happen. So, the way you're going to look at it is, you're going to say, how did we do it last time? Remember what we did? We're going to come right back to here. Going to come right back to right over here and say, wait a minute. There is a range you're going to reach. This ain't going to be this ain't the maximum range. You're going, in this scenario, you're going 5.5 kilometers. You're going 5,500 meters. 5,500 meters as opposed to 17,600 meters. So you're going about, less than a third that distance. You're going less than a third the maximum range. So we're not going 17,600 kilometers. We're going 5,500 kilometers. That'll be the R right there. We do know from all the work that we've done, that we got this. Okay, great. Let's solve for theta somehow. Let me get sine 2 theta by itself for starters. Let me multiply by G. Let's do this. Let me multiply by G on each side and divide by V squared. Let's get this guy by himself. So let's multiply by G over V squared. Let's multiply by G over V squared on each side. Multiply by G over V squared on each side, and you're down to here. This is how you're going to get there. Now, we're going to get two answers here when we do this. Let's see what we can do. Now, we all know it's kind of it's a bit of a complicated matter, maybe yes or no. We already got it in the back of our mind. We know what the sine function behaves like, at least in a kind of a general sense. If this is 180 degrees right here, and this is 0 degrees right here, and this is 90 degrees right here, if you go over this way a bit, x degrees, you'll get a sine value. If you go over the other way, x degrees, because of the symmetry, you're going to get the same magnitude sine value. They are equal. They are equal. This guy's going to, so this is of interest because it's going to help us get to where we need to go. We're going to get two scenarios here. We're going to divide it by 2. Each one of these is going to be 2 theta. In other words, one's going to be 2 theta on the low side, 2 theta sub L, and the other one's going to be 2 theta on the high side. 2 theta sub H, 2 theta sub L. And look at it. Look at it. So we have what we have here, guys. Let's see what we can say. Here's G. G is 9.8. R is 5,500. V squared is 415.31 squared. And, at the end of the day, let's find out what the theta will be. It's probably, the calculator is just going to give you one of them, and then you can play the game a little bit. 2 theta will be the inverse sine of this entire song and dance right here, guys. The 2 theta under consideration, let's talk about it. It's going to be something. If you put 9.8, 5,550, multiply these two, the 9.8 and the 5,550, and divide it by the square of 415.31, divide it by the square of 415.31, get the inverse on it, you're going to get 18.21 degrees. That's got to be on the low side. That can't be the high side, man. There can't be something lower than that. Maybe there is, but I don't think so. If you divide by 2, that's ballpark, 9.1. .1 degrees. Okay, great. Now what? There's a number of ways you can do it. When something gets fired, there's got to be there's a couple ways you can look at this, guys, just to kind of give you the insight on it. Kind of your reference point is this guy, the 45-degree angle. However much underneath the low one is here, is the same amount above the high one is. This amount right here, delta theta and delta theta, they're the same. This is what I mean. If this happened to be if this was a 30-degree angle, how far underneath is a 30-degree angle from a 45-degree angle? 45-degree angle, 30-degree angle, it's 15 lower. 15, you subtract 15 from 45, you get the 30. If you add 15 to 45, you get 60. So the 60-degree angle and the 30-degree angle are the two angles that'll give you the same range. That's one way you can do it. If that's the case, this 9.1 this 9.1 down here, 9.1, is underneath 45 by how much? Close to 36. 35.1. 35.1 under this guy. Then go 35.1 over this guy. 35.1, 45, what did we say? Forgive me. Let me, 35.9 rather, I'm sorry. 35, so it's 35.9 under this guy, the 9.1. The 9.1 is 35.9 under. If it's 35.9 under, then this guy is 35.9 over. What's 35.9 over 45? 45 is kind of like the equilibrium place, if you allow me to say that. For lack of a better convenient word, maybe. At 45-degree angle, 9.1 is 35.9 under. That means for the low guy, theta sub L. Theta sub H is going to be also 35.9, but over the 45, which is going to be 80.9. So let's see what we got here. So that would be 80.9. That's another way to do it. Another way you can kind of say it is they both add up. If one's under by a certain amount from the 45 and the other one's over by a certain amount from the 45, if this is under by delta H from 45 and this is over, then we got the theta L is equal to 45 minus some delta theta. The theta H is 45 plus some delta H. In this case, 35.9. If you add these two, the negative delta H, if you add these two quantities, theta L and theta H, they'll equal 90. Why is that? Because 45 minus delta H and 45 plus delta H, when they're added together, the minus delta H and the plus delta H cancel, you get 90. So these guys, they're going to be complementary. The other guy is going to be 80.9. Well, this one gives you the escape time if you're the soldier. This one gives you the escape, this one gives you the maximum escape time. This one gets there a lot faster. They both add up to 90 degrees. Interesting. I mean, there's a lot of ways you can do it. I don't want to mess you up more than I'm going to help you here. If this is 18.21 right here, you went 18.2. You went from here 0 to here, here to here. So from here to here, it's 18.21. Here to here, 18.21. Okay. If you went over 18.21 that way to get 18.21, go 18.21 that way. Remember, this is the same length. If that's 18.21, this is also 18.21. The symmetry of it dictates what goes on. Take 180 and subtract 18.21, you get 161.79. 161.79, what the heck? We'll call it 161.8. That's 2H. That's 2 theta H. 2 theta H is 161.8. Divide by 2 on each side, that is 80.9. Also getting you 80.9. A lot of ways to go, guys. This is probably an easier way to go. The easier scenario is once you nail one of them, the other one is going to be, if this was delta theta on the downside, this is delta theta on the upside. Another way to do it is when you know one of them, the other one has to be its complement. They have to add up to 90 degrees. Okay, so that's the scenario there. That's B. You've got A, you've got B. Those two are B. They're asking you how the flight times compare. So that shouldn't be too bad. Again, guys, you guys got all these notes here, so you should be all right. I erase it. You can always go back. So let's see what we have. Okay. So what else? So what's going on here? Well, at that point, guys, it ain't that bad. We know a lot. I mean, we know that the total flight time, and we've done this a number of times. We can write it with slightly different notation, but the basic form of it is what it is, guys, and that should be pretty straightforward. The basic flight time is this. If that's the case, look at the theta L. Look at the theta sub L scenario. Theta sub L scenario, and this is the theta sub H. Theta sub H scenario. So we have this. Let's go. Just plug in everything that's got to get plugged in, guys. It's pretty simple as far as that's concerned. Let me just do this. Let's kind of cut to the chase a little bit on the whole thing. You can see this in my notes, but let's just use this as the way to go, and then maybe we can save some time here on the whole process. The scenario here is this is 2 is 2, V is 415.31. And the sine of theta is the sine of 9.1 divided by 9.8. When you do that entire song and dance, you are getting $13.41. Here, you will go again. Here's 2. V is 415.31. The sine of theta here is not the sine of 9.1. It is the sine of 80.9. Sine of 80.9 divided by G. And there you go. You plug in and go. And when you actually grind all that out, not surprisingly, it's going to be a bigger amount of time. T equals 83.69 seconds. Two different scenarios here. As far as flight times are concerned. Yeah, absolutely. Well, yeah, they're going to have the same range. Both of these are going to go the same horizontal distance. They're going to go 5.5 kilometers, 5,500 meters. So let's see here. Let's see some of what's going on here. How far the person's trying to get away from this, I guess you could say. And say, how far is the person going to be able to get away in two different scenarios here? How far can he go? And just for some reason here, he's trying to get away from what is going on here. So let me kind of see here how they said this. It's a little my own notes. I wrote the notes, and I'm kind of confused by my own writing sometimes. Well, let's have a look here. Assume the vehicle retreats at its maximum speed of 80 kilometers per hour. Assume that the vehicle retreats at its maximum speed to be as far from the ensuing explosion as possible. How far is the factory at the time of the explosion for each launch angle? How far is it from the factory? For some reason here, I'm just trying to figure out okay, this is what this explains it. For D, you're going to look at the scenario again. Now you got to be a little just careful what's being asked here. The numbers aren't quite as big as you think they'd be, but they are if you look carefully, to be honest with you. You got the theta sub L is this, and you got the theta sub H is this. I'll tell you what we're going to do. Let's kind of get everybody on the same page on this one. Since we're always dealing with meters, we're always dealing with seconds, let's get out of the kilometers, let's get out of the hours. If they're saying this thing can retreat at 80 kilometers per hour, I'm going to assume just bam, it takes off and it's going to be, it reaches that speed really quickly. If this is 80 kilometers per hour, that's 80,000 meters. 80 kilometers is 80,000 meters. An hour is 3,600 seconds. Let's find that. Basically, this thing's taken off at 22.2. That's 22.2 meters per second. Okay, so it's kind of simple. The way they ask the question's kind of a little. I don't know. It's not. It's actually a good way to ask the question. You got to be careful. Don't just give what you think is maybe a simple answer. Okay, V is this. V is this. Now I'm going to erase this and then write underneath here, and we'll figure out what we're going to say. But if that's the case, how far does the vehicle get from where it fired? From where it fired at 5.5 kilometers away from the target. How far did it get during that time? Well, the vehicle's going 22.22 meters per second. So let me actually get rid of this right now. I mean, let's just keep that in mind. 22.22 meters per second. So what's going on here? Well, it means this. 22.22 meters per second times, for the theta sub L, it's 13.41. Thirteen point 41 seconds. You grind this out, they got about 298 meters away. Well, I got about 300 meters away. I guess that's not bad. I mean, it's something. They got away by that much. How far away are they from where the explosion took place? Well, here's how far he drove away, and the explosion took place 5,500 meters from where he started. He started 5,500 meters away from the objective where the explosion took place, and he got 298 meters away. (5,798 meters, 5.798 kilometers. That's where he's going to be. Depends how they ask you to answer the question, guys. Watch out. Answer the question the way they're asking you. Period. It's the way it is. That's for this guy. That's for this guy. For the guy I got right here. So that's him. What about the other one? What's going on here? Well, it's the same thing. It's 22.2 meters per second. You're not just driving in that scenario. You're not driving a short amount of time for the low angle scenario. You're driving a greater amount of time because you got the high angle scenario that you're with which you're dealing. That's 83.69 seconds. Well, you knock this one out. It's not going to be about 298 meters. It's not going to be about 298 meters, 300 meters. This is about 1,800 meters, 1,900 meters, close to that. It's 1,000 859 and you got that. What does that mean? Well, look, I mean, let's get it straight. I mean, at the end of the day, this was the total X distance away for this guy. Came out to 5,000, almost 5,800 meters, about 5.8 kilometers. The other one is, you take this, 1859.78 plus there's a lot of ways to go here. About 7,360, 7.36. .36 kilometers regarding that. So that's it. I mean, that's not bad. Not too bad. There's a lot here. I mean, a lot out here. It's in the notes. For those of you in the 209, you have it on the notes too in Canvas. Those of you that I might be letting to look at and able to look at this stuff, you got to get a hold. Somehow have a hold of the problems, that hold the book and look at it if you'd like. That way, I have no problem with that. So, I mean, for anybody out there looking at it, obviously you have to have the problem in front of you, is what you have. And so you acquire the book and you look at what's going on, you can see what I'm trying to say here. These are great problems, guys. There's a lot here. I mean, it took forever to kind of get to them, in a sense, but once we've done all these different projectile scenarios to actually have this happen. I think the problem 70 that I had given is also something I'm going to have to do from scratch. I'm not sure what motivates me to kind of pick some of the problems I pick sometimes. You think with all the hundreds of problems that we have already fully solved, but that's all right. It just gives us something else to look at. So we come out of this stronger, I think. We come out of this really well. For number 70, a projectile. Number 70, a projectile is launched up and to the right over flat level ground. Its range is equal to half of its maximum elevation above the ground. What was the angle between its initial velocity and the ground? Ignore air resistance. Okay, after all that we've talked about, all that we've done over a few videos, guys, this almost comes across pretty easy for us. Should be relatively easy for us, guys, when we're doing it. Okay. So let's see what we have. Okay, guys, pretty straightforward stuff for this scenario, actually. The way you want to look at it let's ask it again. A projectile is launched up and to the right over flat level ground. If its range is equal to half its maximum elevation. Its range is equal to half its maximum elevation above the ground. What was the angle between its initial velocity and the ground? Ignore air resistance. This is pretty fascinating stuff, if you ask me. So its range, still a great problem. I mean, its range is equal to half of its maximum elevation above the ground. So this thing gets fired up. That one's V. This is theta. Simple as that. I mean, if I knew how to draw, that'd be great too. But okay, so we got this. And it's kind of, this is definitely not a good drawing. It describes most of my drawings, I think. But I mean, So it's going to come down to here. Assume this thing goes higher. Assume I had a blackboard that was a lot higher, you guys. But they're saying here, that's H. They are saying that a projectile is launched up and to the right over flat level ground. Its range is equal to half its maximum elevation above the ground. What was the angle between its initial velocity and the ground? So its range is equal to half of its maximum elevation. The range x is equal to h over 2. Okay. Is it true that the range x, well, this is kind of interesting in its own right? You know, we got to remember that the range x is v squared sine 2 theta over g. That's x. We know that h just trying to put 2 and 2 together, guys. For some reason, I could have sworn. Yeah, I could have sworn I had that problem. I think I just did it. I've done it cold. The semesters that I've had to do it, I think I have just done it cold. Simple as that. But that's this. So there we go. We got those two scenarios right here. And we're trying to make sense out of that right there. Okay? Well, this is v squared sine 2 theta over g. That's the range. It's equal to h over 2. Let's make sure. Guys, just give me a second. I want to make some careless mistake that everybody's going to regret, especially me. Yeah, it looks pretty good. Everything looks good. Okay, yeah, not a problem. So we're looking like that. That's x, the range, whatever you want to say it. This right here is all of this, h over 2. This whole thing divided by 2 puts a 2g on the bottom. Guys, this is the crux of the whole problem right there. This is what's going to make it happen. Notice the muzzle velocity doesn't really figure into it. It's the proportionality of the situation. You're going to have greater range. Let's put it this way. This is fascinating in its own right. For a situation like this where this reality holds, whatever that theta happens to be, if the muzzle velocity was made, if v was made 4 times bigger, if v was 4 times bigger than it was earlier, you're firing with different projectiles, different gunpowder, different whatever. If v was 4 times bigger than the original v, if you put this is instead of v, this is 4v, whatever, it's going to be 16 times, 4 times greater for the same angle now. Don't change anything. Don't change the angle. Don't change anything. For the same angle, if v was 4 times greater than something else, 4 times greater, 4 times the size that it was earlier, 16 times further will it go if no air resistance. 16 times further would it go if v was made 4 times bigger than it was earlier. Yeah, It'll also go 16 times higher. The curve, the parabolic curve, will be the exact same shape, just bigger. Just bigger. It's going to be 4 times high. The peak will be 4 times higher than it was earlier, and the range will be 4 times more than it was earlier. The math tells you that. The math tells you that. Let's do what we can. Let's multiply by g over v squared. Let's multiply on each side of the equation by g over v squared. Multiply by g over v squared on each side. G over v squared. That's interesting. See what we could say here. I think there's a number of ways we could take this. There's half angle formulas. I don't think we need to go there. Sine 2 theta is 2 sine theta cosine theta. This guy is sine squared over 2. Multiply by 2 on each side and divide by the sine of theta. Multiply by 2 on each side. Multiply by 2 on each side, that's 4. And divide by the sine of theta. So you got this, divide by the sine theta. Now divide by cosine theta on each side. Okay, let me back up. I think everybody understood what I just did, but just in case. If you multiply by 2 on each side, you got this. Just in case, guys, I want to kind of look at it. Let me get another piece of chalk. Multiply by 2 on each side, you get down to here. Divide by the sine of theta on each side. Just slow it down a little bit, I guess. Divide by the sine of theta on each side. You got this. Divide by the cosine of theta on each side. What is the sine of theta divided by the cosine of theta? It's the tangent of theta. Sine of theta divided by cosine of theta is the tangent of theta. Theta is going to equal the inverse tangent of 4 over 1. Yeah, it's going to be a big number. Yeah, it's got to be a big number, guys. You got to remember, if I could draw this better, this is pretty short. This is twice the length. This right there is twice the length of this. Kind of trying to draw to give you the illusion that it's somehow smaller or something. But so that's it. Let's see what we got here. Yeah, 75.964 about. 75.964. Yeah, it makes sense. It ain't going that far compared to how high it's going. It's going twice as high as it's going far. It's going twice as high as it's going far. So let me just kind of just be careful here and let me look at it again. Just in case. Yeah, that's fine. And that's what we're talking about. It's a lot there, guys. Some of these problems take a long time. I mean, they can be done fast. It's a little different challenge if you're trying to teach the material rather than do the material. To do the material, the only person to whom you have to explain anything is to yourself. So it should go a little smoother for you. You got to get the right answer at the end of the day. I mean, that's the big thing they're asking you about. They're not calling you on anything else. They're assuming you're working hard. They're assuming you're being honest, and you're getting the right answer. To a large degree, you're just getting the right answer. The only person to whom you have to prove something is yourself at that point. Even in those circumstances, however, when you're proving something to yourself, rigorously going through it, you can catch yourself making a mistake sometimes, if indeed that happens. Hopefully it doesn't happen, but when mistakes do happen, you can catch yourself if you're being very rigorous in your presentation. The end, when you're showing this stuff to yourself, there's a lot less that you have to do. It's a different dynamic if you're trying to run all over the place and explain something, and that's something you're going to realize. Whatever profession you do, if you're given a presentation, you've got to give that kind of explanation as to what's going on. You got to be very rigorous about it, and you've got to dot every I, cross every T, and you got to explain everything that's going on. If you're given a presentation, either as a professional, as an engineer, as a medical professional, in some capacity as a business professional, or as a teacher, you're going to run it like that. But if you're doing the actual homework and exams, you got to get the right answer at the end of the day, and you got a little bit more leeway, but obviously you have to do it right. So look at the arguments that take place, guys, and how this all happens, and I think we're looking pretty good. That's it. We'll proceed with some other material as well today. I think I'm going to leave it at that. Let me just go over here, and then we'll start something new next time we're together. So